I'm going to try to generate another Taylor series. This time I want to generate a Taylor series for the natural log function centered at x equals 1. This is also a pretty famous one. You may want to memorize this one as well. You'll notice that I'm putting this under the Taylor series definition, and that's because the natural log function isn't defined at 0. And so a logical place to center it, a place that's used a lot, would be to center it at 1, which is where its x-intercept is. Anyway, the basic natural log one that a lot of times people know comes from one centered at 1, again, because it can't be centered at 0 because it's not defined at 0. So technically a Taylor series, not a Maclaurin series. Now you're going to have to get used to generating these things, and you don't want to have to do it the long way that I did it, where you kind of set up that general formula every time, okay? You really want to crank it out using this formula, and you're going to have to get a feeling for how you do that, okay? I make a lot of mistakes and I leave a lot of things out. So I will typically kind of write out the general terms first without actually filling in values, and then I go from there, okay? So I want the 0th derivative, which is just the functional value at 1 divided by 0 factorial, and then I'm going to have that times x minus 1 to the 0 power, which of course is just going to end up being 1. It's going to end up going away, okay? And then I'm going to have the first derivative centered at 1 over 1 factorial times x minus 1 to the first power. And then I'm going to have the second derivative centered at 1 over 2 factorial times x minus 1 to the second power. And then I'm going to have the third derivative centered at 1 over 3 factorial times x minus 1 to the third, and so on. And then I can kind of start dropping things in. But if I don't write that out at the start, again, bad things happen. So you'll have to kind of feel this out and see what works for you. All right, so the function here is f of x equals the natural log of x. You're going to need the first few derivatives here. You may just want to go ahead and find all those derivatives right off the bat. So f prime, of course, is going to be 1 over x. Okay, that's x to the negative 1, which you might want to use to find the second derivative. The second derivative is going to be negative x to the negative 2. Okay, the third derivative is going to be, that would be 2x to negative 3, right? And again, keep in mind with those negative exponents, if you're trying to evaluate these by hand, you may want to turn those into positive exponents and pull them down to the bottom. So I'm going to write this as negative 1 over x squared. Let's see, is that right? Negative x, negative 2. Yeah, and this is going to be 2 over x cubed. Okay, and that might make things a little bit easier. So trying to find the functional value at 1. Functional value at 1 there is going to be ln of 1 is 0. Okay. The derivative at 1 is 1, okay? The second derivative at 1 is going to be equal to, looks like negative 1, okay? And the third derivative at 1 is going to be equal to positive 2. Okay, so let's go ahead and start filling in stuff here and let's see what happens. Okay, f of 1 is 0. And so actually we're just going to have 0 times, and that's going to be 1. This whole term is just going to cancel, okay? So that term's gone completely, all right? The second term, f prime of 1 is just 1 over 1 factorial. 1 over 1 factorial, of course, is really just equal to 1. So actually we don't even need the 1 out there really, but I'm going to put it there, okay? The next one here, the second derivative of 1 is negative 1, okay? So we'll say minus 1, and 2 factorial is just equal to 2. So I'm going to simplify that down to 2, and you're going to see why in a second here. And then the third derivative is 2, okay? And that would be over 3 factorial. Now that's 1 times 2 times 3, which means if you divide a 2 out of the top and bottom, you're actually just going to be left with a 1/3. Okay, and so actually if you continue this a little bit farther, and I'm not sure we've gone far enough to actually see a trend here, but you actually end up with a reasonably simple series. So it turns out the natural log series, Taylor series, centered at 1 is x minus 1 to the first minus 1 over 2, x minus 1 squared, plus 1 over 3, x minus 1 to the third. It's going to be an alternating series, and this pattern is just going to continue. So it would end up being negative 1 to the n power, and again, you're going to have to decide, are you starting at n equals 1 or are you starting at n equals 0? We want it to be positive first, so I think you could do the n power here. Anyway, we're going, that's a 0 power, second power, third power, and so on. Oh, that's not, that's a 1, 2, 3, 4. So actually, yeah, maybe you are starting at n equals 1. You can start these at 1 or 0. Assuming we're starting at 0, it would be x minus 1 to the n plus 1 power, because you need to start it out at 1. And then it would be over that same thing factorial. However, I have a feeling that most textbooks would probably start this off at term 1. And if you start this off at term 1, you want it to be positive. So you might do like an n plus 1 power here, and then you could actually just do that to the nth, and you could do an n factorial. So you'll see different setups, and it kind of depends. If you're doing this in a free response question, you might want to note whether or not you're starting at n equals 1 or n equals 0. So you can kind of get different writings for your general term. But anyway, kind of an interesting pattern here. Alternating series with fractions, basically 1 over n. Oh, I'm sorry, there's no factorial here, just 1 over n. In fact, you don't even need the parentheses here. So anyway, that's a nice example of how you can generate this for just kind of a general series that you haven't seen before. And again, if you just write out the terms of the series, it really can work out very nicely.